Hello, welcome back to AP Biology, Semester 2, and today we are going to Chapter 4, Section 2, talking about carbon atoms and how they can form diverse molecules by bonding to 4 other atoms. The key to an atom's chemical characteristics is its electron configuration. This configuration determines the kinds and number of bonds an atom will form with other atoms. Speaking of formation, let's go to the formation of bonds with carbon. Carbon has 6 electrons, with 2 in the first electron shell and 4 in the second shell. Having 4 valence electrons in a shell that holds 8, carbon would have to donate or accept 4 electrons to complete its valence shell and become an ion. Instead, a carbon atom usually completes its valence shell by sharing its 4 electrons with other atoms in covalent bonds so that 8 electrons are present. These bonds may include single and double covalent bonds. Each carbon atom thus acts as an intersection point from which a molecule can branch off in as many as 4 directions. This tetravalence is one facet of carbon's versatility that makes large complex molecules possible. When a carbon atom forms 4 single covalent bonds, the arrangement of its 4 hybrid orbitals causes the bonds to angle toward the corners of an imaginary tetrahedron. The bond angles in methane, CH4, are 109.5 degrees, and they are roughly the same in any group of atoms where carbon has 4 single bonds. For example, ethane, C2H6, is shaped like 2 overlapping tetrahedrons. In molecules with more carbons, every grouping of a carbon bonded to 4 other atoms has a tetrahedral shape. But when 2 carbon atoms are joined by a double bond, all bonds around those carbons are in the same place. For example, ethene, C2H4, is a flat molecule. Its atoms all lie in the same plane. We find it convenient to write it all structural formulas as though the molecules represented were flat. But keep in mind that molecules are 3-dimensional and that the shape of a molecule often determines its function. The electron configuration of carbon gives it covalent compatibility with many different elements. Okay. Here I have written on the board methane. Methane is the molecular formula for methane, CH4. And its structural formula is here with the hydrogens connecting to the carbon on all 4 sides. Methane happens when a carbon atom has 4 single bonds to other atoms. The molecule is tetrahedral. Tetrahedral, 1, 2, 3, 4. Okay? Ethane. The molecular formula for ethane is C2H6. And this is the structural formula here for ethane. A molecule may have more than one tetrahedral group of single bonded atoms. Ethane consists of 2 such groups, as we can see here. Ethene, or known as ethylene. The molecular formula here, C2H4, and this is its structural formula. When 2 carbon atoms are joined by a double bond, as such here, All atoms attached to those carbons are in the same plane. The molecule is flat. Okay. Here we have the hydrogen, which has one valence. The valences of the major elements of organic molecules are hydrogen, oxygen, nitrogen, and carbon. Valence is the number of covalent bonds in an atom that an atom can form. It is generally equal to the number of electrons required to complete the valence outermost shell. All the electrons are shown for each atom in the electron distribution diagrams. Only the electrons in the valence shell are presented in the Lewis dot structures, which are these here. Okay. Moving on. Let's just have to pull it out when I get there. All right, so here we have the structural formula for urea. Urea and carbon dioxide are molecules with one carbon atom. As you can see here, it only has one carbon. It has nitrogen and hydrogen and oxygen connected to it. Whether we call carbon dioxide organic or inorganic, however, it is clearly important to the living world as the source of carbon for all organic molecules in organisms. Urea, CONH2, is the organic compound found in the urine that Waller synthesized in the early 1800s. The structural formula for urea is shown right here. Again, each atom has the required number of covalent bonds. In this case, one carbon atom is involved in both single and double bonds. Urea and carbon dioxide are molecules with one carbon atom. A carbon atom can also use one or more valence electrons to form covalent bonds to other carbon atoms, linking the atoms into chains of seemingly infinite variety, as we can see for urea. Okay, so let's talk about molecular diversity arising from carbon skeleton variations. All right, carbon chains form the skeletons of most organic molecules. The skeletons vary in length and may be straight, branched, or arranged in closed rings. Some carbon skeletons have double bonds, which vary in number and location. Such variation in carbon skeletons is one important source of the molecular complexity and diversity that characterize living matter. In addition, atoms of other elements can be bonded to the skeleton at available sites. Let's talk about hydrocarbons. All of the molecules that are shown here on the board are hydrocarbons. Organic molecules consisting of one only carbon and hydrogen. Atoms of hydrogen are attached to the carbon skeleton wherever electrons are available for covalent bonding. Hydrocarbons are the major components of petroleum, which is called a fossil fuel because it consists of the partially decomposed remains of organisms that lived millions of years ago. Although hydrocarbons are not prevalent in living organisms, many of a cell's organic molecules have regions consisting of only carbon and hydrogen. For example, the molecules known as fats have long hydrocarbon tails attached to a non-hydrocarbon component. Neither petroleum nor fat dissolves in water. Both are hydrophobic compounds because the great majority of their bonds are relatively nonpolar carbon to hydrogen linkages. Another characteristic of another characteristic of hydrocarbons is that they can undergo reactions that release a relatively large amount of energy. Here, I have up here, this is propane, and it shows the length of the carbon, the hydrocarbon. Then I have here 2-methylpropane, commonly known called isobutane, and this shows the branching of the hydrocarbon. Here is 1-butene. It shows the double bonds and hydrocarbons. And here have cyclohexane, which shows the rings in hydrocarbons. Okay? And as we know that carbon skeletons vary in length, they can be shorter or longer. Here, skeletons may be unbranched or branched, but I show you the branched here. For the double bonds, the skeleton may have double bonds, which can vary in location. The double bonds can either be here, or it can be in the middle, or even here. I would say here. Not here, but I would say here, here, or here. Okay? Which will actually change the function of the skeleton or the molecule. All right? For the double rings, or for the rings, I would say, some carbon skeletons are arranged in rings, and the abbreviated structural formula for each compound. Each corner represents a carbon and its attached hydrogen. All right, now that we've talked about hydrocarbon, let's go on to isomers. Variation in the architecture of organic molecules can be seen in isomers. Compounds that have the same numbers of atoms of the same elements, but different structures and hence different properties. Compare, for example, the 2,5-carbon compounds. Both have the molecular formula C5H12, but they differ in the covalent arrangement of their carbon skeletons. The skeleton is straight in one compound, but branched in the other. We will examine 3 types of isomers: structural isomers, geometric isomers, and enantiomers. Structural isomers differ in the covalent arrangements of their atoms. The number of possible isomers increases tremendously as carbon skeletons increase in size. Structural isomers may also differ in the location of the double bonds. Geometric isomers have the same covalent partnerships, but they differ in their spatial arrangements. The differences arise from the inflexibility of double bonds. The arrangement with both X's on the same side of the double bond is called a cis isomer, CIS isomer. And the arrangement with the X's on opposite sides is called a trans isomer. The subtle difference in shape between geometric isomers can dramatically affect the biological activities of organic molecules. Enantiomers are isomers that are mirror images of each other. Okay. There are some carbons that are called asymmetric carbon, spelled ASYMMETRIC, asymmetric carbon, because it is attached to 4 different atoms or groups of atoms. The 4 groups can be arranged in space around the asymmetric carbon in two different ways that are mirror images. Enantiomers are, in a way, left-handed and right-handed versions of the molecule. Just as your right hand won't fit into a left-handed glove, the working molecules in a cell can distinguish the two versions by shape. Usually, one isomer is biologically active and the other is inactive. Okay. Pharmacists, they deal with enantiomers. The pharmacological importance of enantiomers, example is ibuprofen, which is for pain and inflammation, and albuterol, which is used for asthma. Ibuprofen and albuterol are examples of drugs whose enantiomers have different effects. S and R are letters used in one system to distinguish two enantiomers. Ibuprofen reduces inflammation and pain. It is commonly solid as a mixture of the two enantiomers. The S enantiomer is 100 times more effective than the other. Albuterol is used to relax bronchial muscles, improving airflow in asthma patients. Only R-albuterol is synthesized and sold as a drug. The S form counteracts the active R form. All right. So, the concept of enantiomers is important in the pharmaceutical industry because the two enantiomers of a drug may not be equally effective. In some cases, one of the isomers may even produce harmful effects. This was the case with thalidomide, a drug prescribed for thousands of pregnant women in the late 1950s and early 1960s. The drug was a mixture of two enantiomers. One enantiomer reduced morning sickness, the desired effect, but the other caused severe birth defects. Unfortunately, even if the good thalidomide enantiomer is used in purified form, some of it soon converts to the bad enantiomer in the patient's body. The differing effects of enantiomers in the body demonstrates that organisms are sensitive to even the most subtle variations in molecular agriculture. Once again, we see the molecules have emergent properties that depend on the specific arrangement of their full atoms. This right here concludes chapter 4-2 on carbon atoms and their diverse molecules by bonding to 4 other atoms. The next time we talk, we will be talking about a small number of chemical groups are key to the functioning of biological molecules. See you later. Ta-ta.